In this video, we are going to focus on graphing logarithmic functions. Here are my objectives. Number one, write the inverse function of a given exponential function. And that inverse function is going to be called a logarithmic function. Number two, graph a logarithmic function. And we're also going to be stating those asymptotes, the domain, and the range. And number three, show that exponential and logarithmic functions are inverses of each other graphically. Let's get started. Graph the y equals 2x equation on the coordinate plane below. As we did in the last lesson, we are going to start by making a basic xy chart. So I'm going to substitute these x values into my equation. 2 to the negative 1, or 2 to the negative first, is going to equal 1/2. So when I substituted negative 1 into my function or equation, I'm going to get 1/2. If I substitute in 0, well, 2 to the 0, anything to the 0 we know is 1. If I do 2 to the first, 2 to the first, we all know is 2. 2 to the second, we know is 4. 2 cubed, we know is 8. All right, let's plot those points. So negative 1, 1/2 is going to be about here. 0, 1, 1, 2, 2, 4, and the last one, 2 cubed, which is 8. So if I look at those points, I'm ready to connect them. So let's see what this looks like. It is exponentially growing, but it is also going to level off at my horizontal asymptote. Now, I use that word exponential growth. So exponential growth is when the base here, which is 2, is greater than 1. So since my base is larger than 1, this is a growth function. All right, now, yesterday we talked a little bit about asymptotes. And if I look at my graph here, as my numbers that I plugged in got larger and larger and larger, and this is going to continue if I kept plugging in values like 4 or 5 or 6, my value or my curve is going to increase. If I were to plug in numbers that were smaller than negative 1, the value of that function would get closer and closer to 0, but not quite touch it. So that means my asymptote or my horizontal asymptote is going to be around here on my x-axis, because I know that y, regardless of my input, is never going to equal 0. All right, domain, it's a continuous function, negative infinity to positive infinity. My range, my y values are limited by that asymptote, so I know it's going to be everything larger than 0, not including 0, and goes on in that positive infinity direction. My horizontal asymptote is going to be at y equals 0. Okay, now our job is to find the inverse of this function, and that actually is our first objective. Well, we focused on this in our last unit. So if you remember the steps that we followed, we took the x and the y and we interchanged them. So instead of having y equals 2 to the x power, or 2 raised to the x, we are going to rewrite that expression as x is equal to 2 raised to the y power. So we're interchanging those x and y variables. Now our job is to solve for the new y. Well, let's think about how to do that. We learned in the last section how to change an exponential equation into a logarithmic equation. So if I were to look at that, I can rewrite this as y equals the base of my exponential equation becomes the base of my log. So y equals log base 2. The exponent is always the value that goes on its own. So you can see it was a y equals. And the argument is the one that currently is on the left side of that equation. This is going to be my argument. So I just rewrote this exponential equation as a logarithmic equation, and I did that by finding its inverse. Let me talk through that again. I interchanged the x and the y's, and then I solved for the new y. And again, I solved for the y by switching it to a log. The base of the exponential expression or exponential equation was the base of my logarithmic equation. The exponent in the exponential equation is always alone because the log is equal to the exponent. All right, now let's try to graph this. Well, I'm not quite sure if I know how to graph a log equation when it's in this form, but I think I can actually make an XY chart from this equation. Let's think about that. Well, these I know are the same. I interchanged the X's and Y's. All I did was switch to the form to write it as a logarithm. So if I were to make an XY table for the equation that's in the yellow box, I think I'm going to plug my numbers or my inputs in for the Y. Let's use those same values I did for the equation above. I'm going to substitute in -1, 0, 1, 2, and 3. So again, I'm focusing now on this equation. If I plug -1 in for the Y, well, that means that my X is going to be 2 raised to the -1 power, which is 1/2. If I replace my Y with 0, that means my X is going to be 2 to the 0, which is 1. If I replace my Y with 1, 2 to the first, which is 2, and you get the pattern. 2 to the second, we know is 4, and 2 cubed is 8. Let's plot these points. I have positive 1/2, -1. I have 1, 0. I have 2, 1. I have 4, 2, and 8, 3. And if I connect my points, my graph is going to look like this. In my exponential function, I had a horizontal asymptote at 0. Well, now in my inverse, if I remind myself, I interchanged my x's and y's, which means I am going to have a vertical asymptote at 0. So instead of a y equals, interchanging those x's and y's, this is going to be an x equals. So here is my vertical asymptote. Looking at my graph, my domain is all of my real numbers that are greater than 0, and my range is going to be from negative to positive infinity. I want to compare one more thing before we go to the next example. So we started off with an exponential function. We changed it or found the inverse function by interchanging the x and y and solving for the new y. And if you quickly analyze your table, hopefully you notice that without even doing all that work, finding the new equation, what did we do with our table? We took the x's and y's and we interchanged them. Pretty neat. One more thing. This is objective 3. Show that the exponential and logarithmic functions are inverses of each other graphically. Well, if I take this logarithmic graph and I put it up on this initial coordinate plane that I have, I'm not going to make it blue. I'm going to switch the color maybe to green, but still plotting these points. That would be positive 1/2, -1. It's going to be 1, 0. You're going to have a point at 2, 1, a point at 4, 2, and a point at 8, 3. If we connect those points, our curve is going to look like this, same as it looked in the bottom. And you can see that those two graphs are symmetric over that y equals x line. Start at the origin, slope is positive 1. There's my line of symmetry. Now let's consider the exponential function y equals 3 raised to the x plus 1 power. Well, hopefully you're thinking, I graphed the equation y equals 3 to the x yesterday. Wasn't really that big of a deal. So all I'm going to be doing now is shifting that graph to the left 1, because that plus 1 is with the x. That means it's either going or transforming to the left or to the right. If I'm adding, that means I'm going left 1. So let's make a quick xy chart. When I replace x with -1, I have y is equal to 3, -1 plus 1, which is 0. So I have 3 to the 0. Any value to the 0 is 1. All right, same with the 0. I have y is equal to 0 plus 1. And 0 plus 1 is 1. So this is going to give me 3 to the first, or 3. If I replace that x with 1, I have y is equal to 1 plus 1. Keep forgetting that base. So 1 plus 1 is 2, so that's going to be 3 squared, which is 9. One more time, plugging 2 in, that's going to be y is equal to 3 raised to the 2 plus 1. 2 plus 1 is going to be 3, and 3 cubed is 27. Holy smokes, this is already getting very large. I'm going to ignore this 3 input. Let's plot these points. Negative 1, 1, 0, 3, 1, 9. Already getting way off my graph, so I'm just going to connect these 3 points. And then this continues closer and closer towards 0. All right, horizontal asymptote, since there was no vertical shift, my horizontal asymptote is going to be on that x-axis. So y equals 0. Domain, negative infinity to positive infinity. Range, everything larger than 0. All right. Step 2, find the inverse of the function. Graph it on the coordinate plane below. State its domain and range. Let's think what we did on the last one. Finding the inverse function. So here's my initial function. You interchange the 2 variables. So I'm going to switch that x and that y. I'm going to solve for the new y. Okay, so when you're taking an exponential function and you want to get a value out of that exponent, I'm going to switch this to a log. So this is log base 3 of x equals y plus 1. The number that's in the base of the exponential equation is the value that's in the base of the log. The binomial that's in that exponent goes by itself because, again, a log represents an exponent. And then the x becomes your argument. Solving this for y, I'm going to subtract the 1 over. So one more step. I end up with y is equal to, again, I'm subtracting this 1 over. I'm just going to put the y value on the left. I have log base 3 of x minus 1. So now I'm going to graph this log base 3 of f function. And once I figure out what that is, I'm going to bring it down 1. Well, maybe you're not quite sure how to do that. We haven't spent much time graphing logs. Let's think about the whole concept that we just did, finding the log equation in the first place. Well, we went through and we interchanged the x's and the y's. So if you're not comfortable graphing from this point, you can switch the ordered pairs, or you can go through and have your inputs in this y position. Let's say for this example, we just interchange my ordered pairs. So instead of negative 1, 1, this is going to be 1, negative 1. Instead of 0, 3, I'm going to have 3, 0. Instead of 1, 9, it's going to be 9, 1. And the last pair is going to be 27, 2. Graphing that on my coordinate plane. 1 down 1, over 3, 0, over 9, up 1, connecting these points. Now again, if I were to plug in smaller numbers for my x, I would see that the y values are going down, 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 down towards infinity. If the asymptote for my exponential function was horizontal, y equals 0, my asymptote for my log function is going to be vertical. So this is going to be an x equals 0. Domain is going to be everything larger than 0, but not including 0. Because again, it's limited by that asymptote, and the range is going to be negative to positive infinity. Now, we can draw those on the same coordinate plane and see that symmetry over the y equals x line. We could also look at comparing our domain and range. We didn't talk about that with the last problem. We interchanged the x and the y's to find the log function or log equation, and that also means that you're going to see that in your domain and range. So if the domain was negative to positive infinity, or negative infinity to positive infinity, that's going to line with my range. And my range for my exponential function, 0 to positive infinity, that's going to align with my domain. In the next couple examples, we are going to start with a log function. And we're going to begin just by talking about the basic transformations of a log function. These transformations are the same that we have used for all of our other functions that we have graphed so far in this course. So H tells us about the horizontal movement. So we're looking at this. If H is positive, here's an example. If you have y is equal to, I'm going to ignore all the other variables right now. If H is positive, so let's say you have like a +2. If H is positive, that means we're going to be moving it left. And in this specific example, it means that we would be moving it left 2. If H is negative, say now, same example, where maybe you have an x -2, so you're subtracting, that is going to move it to the right. So it's always going to be whatever that opposite operation is, and you're thinking about how far or what x value would you need to get that back to 0. So here, if you had a +2, 2 minus 2 would get me back to 0. That's why that's going to go to the right 2. And here, if x was a -2, -2 plus 2 gets me back to 0. That's why this is going to go left 2. All right, A. A tells us about the stretching, the reflecting, and the compressing. If the A is negative, that means you're going to reflect the graph over the x-axis. If A is greater than 1, then that means you're going to have a vertical stretch. And if it's between 0 and -1, then that means you're going to have a vertical shrink. So again, that A value is always talking about the size. Are you stretching it? Are you shrinking it? Or are you reflecting it? The K is talking about the vertical movement. So if you're looking at this K, that's going to move us up and down. If A is positive, that's going to be a vertical shift. And that means you're going to be going up. And if K is negative, again, that's going to be a vertical shift, but in this case, you're going to be moving down. Now, for these examples, I actually plotted some points. You hopefully recognize the comparison from the last two examples where I switched the actual given equation, interchanged the x and y, solved for the new y to find the log function. But just to speed this process up a little bit, I actually gave you the initial ordered pairs that you would have if you were just graphing y equals log base 2 of x. Now, if you need more information, you're like, that's just not good enough for me, you can switch this to an exponential function. 2 to the y equals x. Again, you're kind of looking at that canoe. We talked about that. If you want to plug in ordered pairs, you would plug them in for y. Let's just go with the ordered pairs that I gave you, though. Now, when you're graphing a log function, similar to the last two examples, you're going to have a vertical asymptote at 0. And the vertical asymptote at 0 is going to occur when there is no transformation. All right, so let's look at this x plus 3. Well, that's talking about my h. If you're adding 3, that means you're going to go to the left. So if it's x plus 3, this means I'm going to go to the left 3. So I'm going to take all of these points that were graphed for me, and I'm going to move them left 3. So that ordered pair that appears to be at 1/2 -1, if I go left 3, that's going to be left 1, 2, 3. If I take this 1, 0, I'm going to go left 1, 2, 3 as well. This 2, 1 is going to be at now -1, 1. The 4, 2 is going to be at 1, 2. And this one over there appears to me to be a little bit larger over there, maybe at 8. And so if I'm going left 1, 2, 3, it's going to be at 5. All right, how does that make sense to me? Well, I know that when I graph an exponential function, say we started with just a basic 2 to the x, that graph is always going to go through 0, 1. And we talked about that again a couple days ago because my leading coefficient here is 1. If there was an a written, it would be 1, and that a represents that y-intercept. Again, the form that we saw looked like this. All right, now, if you look at how this relates to my log function, it starts initially, instead of 0, 1, it starts initially at the point 1, 0. All right, I had a vertical asymptote at 0. Now that vertical asymptote is going to go left 3 as well, so it's now going to be here. All right, domain and range. My domain is limited by the asymptote, so that means it's going to be from -3 to positive infinity. Range, negative infinity to positive infinity. And again, we said our asymptote is going to be x equals -3 because that is represented by my horizontal transformation. Let's take a look at this one. You were given your initial points, those same points that you were given for your first log, because you were looking at y is equal to log base 2 of x. So now you have two different transformations happening with this problem. This means x minus 1. I'm going to be going to the right 1. And this guy, my plus 3, means I'm going to be going up 3. And I'm going to do those shifts at exactly the same time. So starting with this 1/2 -1, I'm going to go right 1, and I'm going to go up 3. This guy at 1, 0, I'm going right 1 and up 1, 2, 3. My 2, 1, I'm going right 1, up 1, 2, 3. My 4, 2, over to 5, up 1, 2, 3. And it is going to look like this. All right, so if you look at those initial ordered pairs you were given, you can see how it moved to the right and it moved up. Now, I didn't really give myself enough space for my asymptote. If it went right 3, instead of my original asymptote being y equals 0, it should be over here at 1. My right graph looks like it's a little bit too close to that. Actually looks like it overlaps, so I apologize for that. It should be leveling off there at 1. Again, never touching it. It gets closer and closer and closer. So instead of getting closer and closer to 0, it's going to be getting closer and closer to that 1 vertical asymptote. So this one's going to be at x equals 1. Domain now is limited by that vertical asymptote. So it's going to be +1 to positive infinity. And the range is going to be from negative to positive infinity. Again, never limited for the log function. Two more quick examples. If the negative is in front of my log, that represents your a, and that means that I'm going to be reflecting all of my points over the x-axis. So my 1/2 -1 is now going to be 1/2 +1. 1, 0 is going to stay. +2, 1 reflects and becomes +2, -1. 4, 2 reflects and gives me 4, -2. And the same thing here, 8, 3 reflects and it becomes 8, -3. So my original points gave me a logarithmic curve that looked like that. My new ordered pairs, you can see the reflection over that x-axis. Now, if you need to show an XY table to give you a little bit more clarity in terms of what's happening, again, what you're doing there is because you're reflecting it over the x, you are basically multiplying each y value by -1. The domain is going to be from 0 to positive infinity. My range is negative infinity to positive infinity. There is no horizontal shift, so my asymptote is going to stay at x equals 0. All right, last one. You have three things happening here. This x plus 2 means I'm going to go to the left 2. My minus 3 means I'm going to go down 3. And then super exciting, this negative 1, again, is going to be a reflection. Now, I can build off my red graph here because this really represents that reflection already. Like I said, if you'd like to make an XY chart, you can do that. You'd be subtracting 2 from each one of the x's, subtracting 3 from each one of the y's. Or I can build off this first function that I have. In this first graph, I was at 1/2 1. So if my initial point was at 1/2 1, I'm now going to go left 2 from there, left 1, 2, and I'm going to go down 1, 2, 3. All right, second one. My next point was at 1, 0. And again, I'm building off of this guy. If it's at 1, 0, I'm going to go to the left 2, and I'm going to go down 3. Next one, starting off at 2, negative 1. So if I start at 2, negative 1, from this point now, again, I'm going left 2, and I'm going down 1, 2, 3. Next one, I was at 4, negative 2. If I'm starting at 4, negative 2, I'm going to go left 2, boom, boom, down 1, 2, 3, puts me here. And the last one was at 8, negative 3. So now starting at 8, negative 3, I'm going to go to the left 2 and down 1, 2, 3. So when I went left 2, that moved my vertical asymptote from x equals 0 to x equals negative 2. So I'm going to have this vertical asymptote here. And my graph now, again, was reflected. So it looks similar to the red curve I have. It was shifted from that original position. All right, domain's going to build off the asymptote, so that's going to go from negative 2 to positive infinity. Range, negative infinity to positive infinity, and the asymptote would be x equals negative 2. If that's a stretch for you, like I said, you can make an XY table from your original points. The reflection is going to be over the y-axis, so you're multiplying all your y values by negative 1. Then you would be going left 1 or left 2 or subtracting 2, and down 3 or subtracting 3.